Attention is all you need. Part 5. The supporting components. We've seen the star of the show, attention, but even the best lead actor needs a supporting cast. In this part, we'll look at three simpler but essential components that make the transformer work: position-wise feed-forward networks, embeddings, and positional encodings. In addition to the attention sublayers, each layer in both the encoder and decoder contains a fully connected feed-forward network. This is the simpler part of the architecture. Think of it as a straightforward processing unit that refines each token's representation. Here's what makes it special. It's applied to each position separately and identically. That position-wise part is important. The same feed-forward network is applied to each token independently. It does not look at other tokens. It just transforms each one on its own. How it works. The network consists of two transformations with an activation function in between. Let's break it down in plain English. First, take the input. In the base model, this is a 512-dimensional vector for a token. Then three things happen. First, transformation. Map it up to a higher dimension, 2048 dimensions. Then comes the activation. The model applies something called ReLU. That's R-E-L-U, short for rectified linear unit. This is a simple rule. If a number is negative, make it 0. Otherwise, leave it alone. The rectified part just means we're removing the negatives, rectifying them to 0. This introduces non-linearity, which helps the network learn more complex transformations. Second transformation. Map it back down to 512 dimensions. Think of it like reshaping clay. You start with a small lump, expand it into a bigger workspace where you can shape it more freely, then compress it back down into the standard size, but with the improvements baked in. Why expand and contract? Why go up to 2048 and then back down? Because it gives the network more working space. By temporarily expanding into a higher dimensional space, it has more room to learn useful transformations before returning to the standard 512-dimensional format used throughout the model. It's like how a chef might spread ingredients across a large counter to work with them more effectively, then plate everything neatly at the end. A key detail about consistency. Within a single layer, the same feed-forward network is applied to every token. But different layers have different feed-forward networks. So Layer 1 has its own parameters, Layer 2 has its own, and so on. Each layer learns its own way of refining representations. Now let's move on to how the model handles the conversion between words and numbers. Embeddings and softmax. Turning words into numbers and back. Here's the fundamental problem. Computers don't understand words. They only work with numbers. So we need two things: a way to convert tokens into numbers going in, and a way to convert numbers back into token predictions coming out. Input embeddings, tokens to numbers. The transformer uses learned embeddings to convert input tokens into 512-dimensional vectors. What's a token? Often it's a full word, but many systems break words into smaller pieces, sometimes called subwords. For example, unhappiness might become un and happiness, so the model can reuse patterns like prefixes and suffixes. These embeddings aren't designed by hand. They're learned during training. As the model sees more data, it learns useful numerical representations for tokens. Tokens that behave similarly or appear in similar contexts tend to end up close together in the embedding space. As an intuition, king and queen might end up close together. Cat and dog might end up close together. However and but might be close, because they often play similar roles. Think of it like plotting cities on a map, but instead of geography, you place them based on meaning and usage. Similar cities end up near each other. Output embeddings, the decoder's input side. The decoder also uses embeddings when it reads the tokens it has already generated. So the model is always working with vectors, not raw words. The final prediction layer. At the very end of the decoder, there's a learned linear transformation and a softmax function. This converts the decoder's final 512-dimensional output into predicted probabilities for the next token. It's essentially asking, given everything I've processed, what is the probability of each possible next token? And in practice, that means choosing from tens of thousands of possible tokens in the vocabulary. The model might say 90% chance the next word is cat, 5% chance it's dog, and so on. Weight sharing, a clever efficiency trick. Here's an interesting design choice from the paper. The model shares weights between the embedding layers and the final prediction layer. Instead of learning separate sets of token representations for input, for output, and for prediction, it reuses the same underlying weight matrix. Why do this? It's more efficient, and it tends to work well. If a token has a useful representation in one place, it's useful everywhere. There is one twist. In the embedding layers, the paper scales the embeddings by multiplying by the square root of D model. In the base model, D model is 512, so the square root of 512 is about 22.6. This scaling helps keep the magnitudes in a good range during training. It's a small detail, but it matters for keeping the numbers well behaved as they flow through the network. Now, we come to one of the cleverest parts of the whole architecture. Positional encoding, teaching the model about order. Here's a crucial issue. The transformer can process tokens in parallel, and attention can connect any positions. But if you don't explicitly inject position information, the model has no built-in sense of order. So, the cat sat on the mat, and the mat sat on the cat could look far too similar because they contain the same tokens, just rearranged. The model would have no way to tell them apart. The solution is positional encodings. We inject information about where each token appears in the sequence. How positional encoding works. The approach is simple. We add positional encodings to the token embeddings at the very bottom of the encoder and decoder stacks. These positional encodings have the same dimension as the embeddings, 512 in the base model, so they can be added directly. So you can think of it like this. The token embedding tells you what the token is. The positional encoding tells you where the token is. Add them together, and the model starts with both what and where. It's like labeling photos with both their content and their timestamp. You need both pieces of information to make sense of the full picture. Why sine and cosine functions? There are different ways to encode position. One option is to learn positional embeddings during training, the same way you learn word embeddings. But the authors chose a different approach. They use sine and cosine functions at different frequencies. Each dimension acts like a wave. Some dimensions change quickly as position changes. Some dimensions change slowly across longer spans. Together, they create a unique fingerprint for each position. Think of it like a barcode, where different stripe widths combine to represent a unique pattern. Position 1 has a certain pattern, position 2 has a slightly different pattern, and so on. No two positions have exactly the same pattern. Why this specific approach? The authors chose sine and cosine for two practical reasons. First, it helps with relative position reasoning. The mathematics of sine and cosine makes it easier for the model to learn relationships like, this token is 3 positions after that token. If you've studied trigonometry, You might remember that sine and cosine have nice properties when you shift them. Those properties help the model understand relative distances between positions. Second, it can generalize to longer sequences. If you train on sequences up to a certain length, learned positional embeddings only exist up to that length. But with sine and cosine, you can compute a positional encoding for any position you want, even beyond what the model saw during training. So if you train on sentences up to 100 words, but then test on a sentence with 150 words, the sine and cosine approach still works. Learned embeddings would struggle there. The authors report that learned positional embeddings and sine and cosine positional encodings perform very similarly on their tasks, so sine and cosine is a neat choice with a practical upside. Now let's see how all these pieces fit together. Let's trace the complete flow now that we understand all the components. I'll walk through the encoder side first, then the decoder side. Input side, the encoder. First, tokens are converted into 512-dimensional embeddings. So, the cat sat becomes 3 vectors. Then positional encodings are added, so the model knows order. Now the first vector knows its first, the second knows its second, and so on. That combined representation flows up through 6 encoder layers. In each layer, the model applies multi-head self-attention, then the position-wise feed-forward network. And remember, residual connections and layer normalization are wrapped around each sublayer, keeping things stable. By the time we reach the top, the encoder has produced a rich, context-aware representation of the input. Output side, the decoder. The decoder takes the tokens it has generated so far, embeds them, and adds positional encodings. That flows up through 6 decoder layers. Each layer applies 3 operations. First, masked self-attention over what's been generated. Second, encoder-decoder attention to look back at the input. Third, the position-wise feed-forward network. Again, residual connections and layer normalization throughout. Finally, at the very top, the linear layer and softmax convert the final representation into probabilities for the next token. The model selects the next token, and the whole process repeats until it generates an end token. So that's the complete picture. And here's what I find most striking: the beautiful simplicity of it all. Every component plays its role. First, attention handles relationships between positions. It's the mechanism that lets words talk to each other, near or far. Second, feed-forward networks refine representations at each position independently. They give each token a chance to process what it learned from attention. Third, embeddings bridge the gap between tokens and numbers. They let us work with words in a mathematical framework. Fourth, positional encodings preserve word order. Without them, the model would have no sense of sequence. And finally, residual connections and layer normalization keep the deep stack trainable and stable. They're the unsung heroes that make everything else possible. It's an elegant architecture. Each piece is relatively simple, but together they create something powerful enough to reshape natural language processing. Think about what we've covered across these 5 parts. We started with the problem. Sequence models were too slow, and long-range dependencies were too hard. We looked at the attempts that came before. RNNs, convolutions, earlier attention ideas. We saw the transformer's overall structure in Part 3. We understood attention itself in Part 4. And now, we've seen how the supporting components complete the picture. The transformer isn't magic. It's a clever combination of well-chosen components, each solving a specific problem. Attention for relationships, feed-forward for refinement, embeddings for representation, positional encodings for order, and all of it wrapped in techniques that make deep learning stable and efficient. Coming up in Part 6, we'll look at why self-attention wins, comparing computational complexity, parallelization, and path lengths across different architectures. This is where the advantages become concrete, not just conceptual. We'll see the numbers that explain why the transformer became the foundation for modern AI.